I am going to start module 3 of chapter 4. In module 2 of chapter 4, I have discussed about solution of two-dimensional Laplace equation, but two-dimensional Laplace equation arises in some particular situations. Thus, it is more realistic to study three-dimensional Laplace equation. Thus, in this module, we shall solve a three-dimensional Laplace equation. It is to be noted that in reality, we need to solve Laplace equation for many geometrical problems. For example, if there is an experiment in a box, we need to consider Cartesian coordinate systems. And if there is an experiment in a pipe, we have to consider, or it is convenient to use cylindrical coordinate systems. Therefore, it is necessary to find solution of Laplace equation taking different geometrical problems or in different coordinate systems. Thus, in module 3 of chapter 4, we shall discuss about solution of Laplace equation in Cartesian coordinate system, cylindrical coordinate system and spherical polar coordinate system. First, I shall discuss about Cartesian coordinate system. For that, now we have to go to the slide show. As I have told, we want to find solution of a three-dimensional Laplace equation in different coordinate systems. I shall use the technique, the separation of variables method, to find the solution. Now, the Laplace equation in Cartesian coordinates can be written as grad square psi, which is equals to del square psi del x square plus del square psi del y square plus del square psi del z square equals to 0. In the method of separation of variables, we assume the solution psi as product of three functions capital X, capital Y, capital Z, where x, y, z are functions of small x, small y and small z respectively. Now, if we substitute solution 2 in equation 1 and we get an equation which is written in equation number 3. So, if we observe this equation, we wrote the equation in terms of y and z term in the left hand side of equation 3 and the term involving the variable small x is written in the another side. That means, in this equation we are separating the variable x from the variable y and z. Let lambda 1 square is the separation constant. So, if we equate 1 by x d2x dx square is equal to minus lambda 1 square, we get the ordinary differential equation which is written here d2x dx square plus lambda 1 square x equals to 0. And we can find solution of this ordinary differential equation easily, and the solution is written here capital X is equals to C1 cos lambda 1 x plus C2 sin lambda 2 x, where C1 and C2 are the constant of integration. Now, if we go back to equation number 3, then lambda 1 square is also equals to 1 by y d2y dy square plus 1 by z d2z dy square. Now, our target is to separate the variables or the function capital Y and capital Z. For that purpose, we take this expression 1 by capital Z d2z dz square minus lambda square on the left hand side, and its value is equal to minus 1 by y d2y dy square. Now, let us choose another separating constant lambda 2 square. So, if we equate d2y minus 1 by y d2y dy square equals to lambda 2 square, we get an ordinary differential equation which is written here d2y dy square plus lambda 2 square y equals to 0, and we can easily write the solution of this equation which is written here. Capital Y is equals to C3 cos lambda 2 y plus C4 sin lambda 2 y, where both C3 and C4 are constants. Now, there is another equation in the dependent variable capital Z which is written here d2z dz square is equal to lambda 3 square into z, where lambda 3 square equals to lambda 1 square plus lambda 2 square. So, now we solve this equation, the z equation, and the solution of z equation can be found easily, which is written here. Capital Z is equals to C5 cos hyperbolic lambda 3z plus C6 sin hyperbolic lambda 3z, where C5 and C6 are constants. Therefore, solution of Laplace equation in Cartesian coordinate can be written in the form psi equals to, which is product of capital X, capital Y and capital Z. So, it is written here in equation number 4. Now, I shall consider one example where Laplace equation comes in Cartesian coordinates. So, here is that example. Find the potential function psi in a rectangular box defined by 0 less than equals to x less than equals to a, 0 less than equals to y less than equals to b, 0 less than equals to z less than equals to c. If the potential is 0 on all sides and bottom, while psi equals to f on the top of the box. So, you think about a rectangular parallelepiped where all the bounds of the parallelepiped are kept in 0 temperature except the plate z equals to c. So, we can write the boundary condition like this. If psi represent the potential function, which is function of x, y and z. So, psi at x equals to 0 is equal to 0, psi at x equals to a is equal to 0, psi at y is equal to 0 is equal to 0, psi at y is equal to b is equal to 0, and psi at z equals to 0 is 0, but psi at z equals to c is a function of x y which is represented by the function small f. Now, we are going to solve this problem together with the supplied boundary conditions. We have already derived the solution of Laplace equation in Cartesian form which is written in equation number 4. Now, if we apply the boundary condition psi at x equals to 0 and psi at x equals to a equals to 0, the equation number 4 reduces to C1. So, here we put x equals to 0. So, if we put x equals to 0, it becomes C1. So, psi at x equals to 0 implies C1 equals to 0, and the other condition psi at x equals to a equals to 0 gives that C2 sin lambda 1 a equals to 0. Now, C2 cannot be 0 because we already got that C1 is 0, but C2 cannot be 0. If C2 is 0, then psi becomes 0 for all x, y, z. So, that is a trivial solution, but we are not interested in trivial solution. So, we assume that C2 is not equals to 0. Therefore, to satisfy the second boundary condition, we have sin lambda 1 a must be equals to 0. Now, sin lambda 1 a equals to 0 implies lambda 1 a must be equals to some m into pi, where m is some integer, positive integers. From here we get that lambda 1 can take the values m pi by a, where m is a positive integer. Now, think about the third boundary condition, this one psi x 0 z equals to 0. So, if we apply that condition here, so here we have to put y is equal to 0. So, if we put y is equal to 0, then it becomes, the second expression becomes C3. So, psi at y is equal to 0 implies C3 equals to 0. So, we get C3 equals to 0, and in the similar way, if we apply this boundary condition psi x y is equal to b z equals to 0, then it will give sin lambda 2 b equals to 0. So, C4, with the similar argument we can say that C4 cannot be 0, otherwise it will give a trivial solution. So, we get the only option to satisfy the boundary condition is sin lambda 2 b equals to 0. So, it implies that lambda 2 b must be equals to n into pi, where m is an integer, or in other words we can say that lambda 2 can take the values n pi by b, where n is an integer. Now, we have two more boundary conditions. The condition psi x y 0 equals to 0 leads to the condition C5 equals to 0. So, if we use that condition and put C5 equals to 0, we find that the solution reduces to the form psi equals to C2 sin lambda 1 x, C4 sin lambda 2 y, C6 sin hyperbolic lambda 3 z, or we can write these three constants together as constant a. So, psi is equal to a sin lambda 1 x, sin lambda 2 y, sin hyperbolic lambda 3 z, where capital A is C2 C4 into C6. Now we have one condition. Now we note that in this solution, this lambda 1, lambda 2 are not arbitrary. They can take the values m pi by a and n pi by b respectively, and lambda 3 is dependent on lambda 1 and lambda 2 by the relation lambda 3 equals to square root of lambda 1 square plus lambda 2 square. So, if we substitute the values of lambda 1 and lambda 2, we get the values of lambda 3 as pi into square root of m square by a square plus n square by b square. And you can see that the values of lambda 3 depends on the values of m and n. That is why we wrote lambda 3 as lambda m n. So, the solution becomes a m n sin m pi x by a sin n pi y by b into sin hyperbolic lambda m n z. And since this is a linear differential equation, the principle of superposition can be applied. Therefore, psi can be written as sum over m, sum over n, a m n into sin m pi x by a sin n pi y by b into sin hyperbolic lambda m n z. Now, you have to remember that there is one boundary condition left. So, to satisfy that boundary condition, and that boundary condition is psi x y c equals to f x y. Now, if we apply this boundary condition to our solution, which is written here, we get f x y is equal to sum over m, sum over n, a m n into the expression is given here. So, if you see this expression, you can see that this is very known series, and this is called the double Fourier series. So, the coefficients a m n can be obtained in this way. We have to multiply this series with sin m pi x by a into sin n pi y by b from in both sides, and then integrate over 0 to a and 0 to b. That will give the values of m n through this relation. And to find the values of a m n, we have to use the orthogonality property of sine functions. So, using that property, we can find the values of a m n, which is given here. Thus, the solution of our problem is psi equals to sum over m, sum over n, a m n sin m pi x by a sin n pi y by b sin hyperbolic lambda m n z, where these sum are for m equals to 1 to infinity, n is from 1 to infinity, and this lambda m n is given here pi into square root m square by a square plus n square by b square, and a m n can be determined from the relation which is given here. Thus, this is our required solution in Cartesian coordinate system. Now, I am going to solve Laplace equation in cylindrical coordinate system. In cylindrical coordinate system, Laplace equation is written in the form which is given in equation number 5. Here we shall use the same technique, the separation of variables method, to find the solution. For that purpose, we have written psi as product of functions capital R, capital theta and capital Z, where R, theta, Z are functions of small r, small theta and small z respectively. So, if you substitute the expression for psi from 6 to equation 5, we get the equation which is written in equation number 7. So, our aim is to separate the variables. So, for that purpose, first we separate the variable z and we assume that the separation parameter is minus m square. So, the equation for z becomes 1 by z d2z dz square equals to m square, and its solution can be written easily. Capital Z equals to C5 e to the power mz plus C6 e to the power minus mz, where C5, C6 are constants. So, from equation 7 we have already separated the variable z, but we need to separate the variable r and theta. So, for that purpose we assume 1 by theta d2 theta d theta square equals to minus n square. So, here n square is the another separation constant. So, the equation for theta becomes d2 theta d theta square plus n square theta equals to 0, and its solution is theta equals to C3 cos n theta plus C4 sin n theta, where C3 and C4 are constants. But there is another equation which is equation in R, and the equation is written here d2r dr square plus 1 by smaller dr dr plus m square minus n square by r square capital R equals to 0. And this is very famous equation, and this equation is known as Bessel's differential equation, and we know that the solution of Bessel's differential equation is the Bessel function. So, the solution is written as capital R is equal to C1 Jn Mr plus C2 Yn Mr, where Jn and Yn are Bessel's functions of order n and of first and second kind respectively. Therefore, the solution of Laplace equation in cylindrical coordinates becomes psi equals to product of capital R, capital theta and capital Z, and these are the expressions for capital R, capital theta and capital Z. Now, we want to solve a physical problem where we can use cylindrical coordinate system. So, this is the example. A homogeneous thermally conducting cylinder occupies the region 0 less than equals to r less than equals to a, 0 less than equals to theta less than equals to 2 pi and 0 less than equals to z less than equals to h, where small r, small theta, small z are cylindrical coordinates. And the boundary conditions are like this: the top plane z equals to h and the lateral surface r is equal to a are held at temperature 0, while the base z equals to 0 is held at 100° temperature. And we also assuming in this problem that there is no source of heat generation within the cylinder. So, we have to find for this problem the steady temperature distribution within the cylinder. So, from this problem and the supplied boundary problems, we can write the problem in this way. The temperature, we have to find the temperature psi, which is a single valued function, and this is for steady state, and this psi will satisfy the Laplace equation grad square psi equals to 0, where 0 less than equals to r less than equals to a, 0 less than equals to theta less than equals to 2 pi, and 0 less than equals to z less than equals to h. And the boundary condition is given that psi equals to 0 at z equals to h and psi is equal to 0 at r equals to a. And there is third boundary condition, which is psi equals to 100 at z equals to 0. So, from the boundary condition, we can note that the solution cannot depend on the variable theta. So, it can be assumed that the solution is independent to theta. Also, it is to be noted that from the general solution, you can see that there is a term YNMR, which is Bessel function of order n and of second kind, and this Bessel function has a singularity at r equals to 0. Since in this physical problem there is a point r is equal to 0, so yn is not defined at r equals to 0. Thus, we need to omit the term yn, and the solution is independent to theta. So, to make it independent to theta, we must have to take n equals to 0. Therefore, from the general solution, we can write the solution for this particular problem as psi equals to C1 J0 MR into C5 e to the power mz plus C6 e to the power minus mz. So, that solution is written here, but we have adjusted the constants in this way. This is A, J0 into A e to the power mz plus B into e to the power minus mz. Now, if we use the boundary condition psi equals to 0 at z equals to h, then we get the relation between A and B as B equals to minus A e to the power 2 mh. So, substituting the value of B in the solution psi r z, we get A j0 e to the power mh e to the power m z minus h minus e to the power minus m z minus h, or it can be written in the form psi equals to B j0 sin hyperbolic m into z minus h, where B equals to 2a e to the power mh. Now, we need to satisfy another boundary condition, which says that psi equals to 0 at r equals to a. So, it gives j0 ma equals to 0. So, this is a Bessel function of order 0. So, it has infinitely many positive roots. Let those roots are xi k. So, we can write the value of ma as xi k, or m equals to xi k by a, where k equals to 1, 2 dot dot. Therefore, using the principle of superposition, we can write the general solution as psi equals to sum over k b k j0 xi k r by a sin hyperbolic xi k z minus h by a. Now, the another condition is psi equals to 100 at z equals to 0. So, it gives the relation 100 equals to sum over k b k j0 xi k r by a sin h minus xi k h by a, and this is again a Bessel series. So, to find the coefficient of Bessel function Bk, we need to multiply the relation with J0 xi L r by A into r from the both side, and if we use the orthogonality property of Bessel function, we obtain the relation which is written here 100 times integration 0 to a r J0 xi k r by A dr equals to Bk sin hyperbolic minus xi k h by A into a square by 2 j1 square xi k. Here we have used the orthogonality property of the Bessel function. That property is written in this slide. You can see that there is the term alpha I alpha j. So, these alpha I alpha j are the roots of the equation j n x equals to 0. And we know the relation that integration of x j0 is j1. So, if we use this property, we can replace the integration in the left hand side here by j1. So, replacing that, we get the relation which is written here. So, from this relation we can easily find the value of Bk. So, it is written here. So, the solution of the given problem becomes psi equals to sum over k Bk j0 xi k r by A sin hyperbolic xi k z minus h by A, where these Bk are given by the relation this. So, these are the values of Bk. So, that solution is written here, and you have to remember that these xi k are the roots of the equation j0 xi equals to 0. Now, I am going to discuss the solution of Laplace equation in spherical polar coordinate system. The Laplacian in spherical polar coordinate system is given in equation number 9. Here we are applying the same method, the method of separation of variables to find the solution. So, first we are separating variables r and the variable theta phi. That means, we are separating the variable r from theta and phi. So, that is given by the relation 10. So, if you substitute 10 in 9, we obtain the equation which is written in equation number 11. So, from this equation we are separating the variable capital R from theta and phi. So, in this way we are separating, and we are assuming that lambda is the separation constant. Now, equating the expression for R which is written here is equal to minus lambda, we get the equation for capital R which is written in equation number 12. And if you see, this is famous Cauchy-Euler equation. So, the solution of this equation can be assumed in the form capital R equals to R to the power m, and this small m can be determined from the value of lambda. So, for convenience, we assume lambda as minus n into n plus 1. So, substituting this value of lambda, we obtain two values of m as n and minus n plus 1. Thus, the solution of R equation or the solution of equation 12 is capital R is equal to C1 R to the power n plus C2 divided by R to the power n plus 1. Now, we have to find solution for capital F which is written in equation number 13. We have already assumed the value of lambda as minus n into n plus 1. So, we are putting the value of lambda here. Now, we are again applying the method of separation of variables So, we are writing f as product of capital theta and capital phi, and we are substituting 16 to 15 to obtain a relation which is written in 17. Here we are separating the variables phi and theta from this relation in this way. So, in the left hand side we have only the function of phi, and right hand side it is only the function of theta, and to equate this left hand side is equal to m square and this expression is equal to m square, and we get two equations which are written here. So, from the phi equation we can obtain the solution easily, as phi is equal to C3 cos m phi plus C4 sin m phi, where C3 C4 are constants, and if m is equal to 0 we get axisymmetric case. That means for that case, if m is equal to, see the equation number 18, if we put m is equal to 0 in this equation, capital phi becomes a constant. That means for that case solution does not depend on the variable phi. So, this case is called the axisymmetric case. Now, this is the equation for capital theta, and from this equation we substitute, we make a change in the independent variable through this relation mu is equal to cos theta. So, if you substitute this in this equation in terms of the independent variable mu, we obtain the equation which is written here. And if you see this equation, this is Legendre equation, but there is some extra terms here, and we know that solution of this equation is the associated Legendre function. Therefore, solution of that equation can be written as linear combination of two Legendre function, associated Legendre function, which is written here theta mu as C5 P n m mu plus C6 Q n m mu, where P n m and Q n m are associated Legendre function of first and second kind respectively, or in terms of theta we can write the function in this way, which is written in equation number 19. Thus, the general solution of Laplace equation can be written in this way: psi equals to sum over m sum over n, C1 r to the power n plus C2 r to the power n plus 1 into C3 cos m phi plus C4 sin m phi into P n m cos theta. In particular, for axisymmetric case it does not depend on phi. So, the general solution can be written as psi, which is function of only r and theta. So, it is sum over m sum over n, C1 r to the power n plus C2 divided by r to the power n plus 1 P n m cos theta. Now, I shall discuss a physical problem where spherical polar coordinate comes. So, this is the problem. We have to find the value of psi at any point in the interior of a sphere r equals to a, such that its Laplacian is equals to 0 over this region, and the boundary condition is psi at r equals to a is given by the function small f. Now, if we look at the general solution of the spherical polar coordinate, which is written in equation number 20, from this solution we want to derive the solution of this problem which satisfies the given boundary conditions. Since r is equal to 0 is a point within the sphere, so the solution must exist at r equals to 0. But if you see the general solution, this solution does not exist at r equals to 0 if C2 is not equals to 0. So, we take C2 equals to 0. So, the solution can be written in this form. So, only r to the power n term is there and all other terms are present, which is written in equation number 22. Now, to satisfy the boundary condition, we have to put r equals to a and value of psi is a. So, if you substitute this, if you satisfy this boundary condition, we obtain the relation which is given here. Now, to find the values of Amn and Bmn, you can see that this is a double series of Fourier and Legendre function. So, to obtain Amn and Bmn, first to obtain Amn, you have to multiply this relation with cos m pi into p n m mu and then integrate over -1 to 1, 0 to 2 pi this. Then you get, now using the orthogonality property of the Legendre function, associated Legendre function, we can write the value of -1 to +1 p n m mu square d mu, and all other terms will be 0 due to orthogonality property, and here also only cos m pi term will be there, all other terms will be 0 due to orthogonality property of Fourier modes. So, using those property we can obtain the values of A and M. This is the expression. So, we get integration -1 to 1, 0 to 2 pi f p n m mu cos m pi d mu d phi is equal to 2 pi a to the power n A m n m plus n factorial divided by 2n plus 1 n minus m factorial. So, from this equation we can obtain the value of m n easily. Similarly, to obtain the value of b m n, we need to multiply both sides with the expression sin m pi and p n m mu. So, that will give the expression for b m n, so which is written here. So, we can obtain both a m n and b m n in this way. Thus, the solution becomes psi is equal to, which is written here. We can make a simplification like this. We can write the cosine function and sine function together to make it as cos of m chi minus phi. So, this is our final solution or the required solution of the given problem. Thus, in module 3 of chapter 4, we have discussed about solution of 3-dimensional Laplace equation in Cartesian coordinate system, cylindrical coordinate system and spherical polar coordinate system. We took 3 examples for 3 different cases, and for all the cases we considered Dirichlet problem. For Cartesian coordinate system, the solution is double Fourier series. For cylindrical coordinate system, the solution is Bessel Fourier series, and for spherical polar coordinate system, we obtain Fourier Legendre series. Thus, we end module 3 of chapter 4.